we have what they call elements. These elements here, you can name as many as possible from hydrogen and so on. But you see that these elements have what they call electrons. And those electrons they do have, there is a certain way they are arranged within those given elements here. And this one gave us things that you need to know before we go to chemical bonding. We talked about electron configuration. Electronic configuration. This is what shouldn't be scaring you at any one time. Configure, the word configure comes from English. Configure is to see how you arrange something. It's a certain pattern, as though the same way you put your clothes in a suitcase, the same way you put the utensils within their trays, and you know that these cups must be in this way. That's a pattern. You're following a particular pattern. So electronic configuration, you're saying that how do you arrange accordingly the electrons within the energy levels of a given atom or element? That's what we're saying. So now, how are they connected to bonding? What I'm talking about. Here, we see that when you look at the way electrons are arranged, they give a lot to be desired for. They give something more to say, how do I arrange them accordingly? Because I remember I've talked about the periodic table. We see that these elements here, I'm just writing things that you must be remembering now, because we might not go deep down into them. So before you go to chemical bonding, you should remember electronic configuration. You should be comfortable with what? Elements. And also another thing we shall be talking about, we shall talk about valencies and more, but you shouldn't be so scared. So we are saying that whenever you keep on putting electrons onto the different levels of a given atom, we say that these elements are quite so ambitious. They always aim to having their levels to be fully filled, or to attain what they call a stable electronic configuration. Stable electron configuration. Allow me to use EC to represent electronic configuration. What we call an stable electronic configuration. You say that here, all the levels, the energy levels of a particular atom are fully filled with electrons. So these elements aim at having what? Stable electronic configuration, or at attaining it, where every single level they must possess must be having electrons to maximum capacity. How do they do it? There are so many ways. Why? How do I know that they attain it? You have to first know, how do I arrange them? For example, let me give you an example here. We have hydrogen that has one electron. We have lithium. Okay. Let me just use lithium. I'm going to pick a selected few. Lithium here. Let me go to carbon, 6. I have sodium, 11. I have aluminium, I say 13. Like that, huh? So let me say, okay, what can I have? Okay. Sulfur. All these are elements here to just remind you about electronic configuration. We say that the rules of the game were, how do I put these electrons here? This one has 11. The numbers that I put here represent the electrons these elements do have. How do I put them into, how do I arrange them? We say that the first level is like filling a house or a flat or building. We say that when you're writing electronic configurations, we say that the first floor takes a maximum of 2. Takes a maximum of 2. The rest takes a maximum of 8. You guys recognize normal English. When you're filling up these energy levels, we are saying that the first room takes a maximum number of people, 2. Before you fill other rooms, you must ensure that the first one is filled. When you go to the next room, ensure that the next room is first completely filled before you go to the third room. So what happens here? When I look at hydrogen, hydrogen has a single electron. So meaning that this one is capable of fitting in the first room. Though the room is not complete, but it's capable of being there alone, because the maximum number the first room can carry is only 1. When I go to the next one, we have lithium. Lithium has 3 electrons in the different rooms. We say that the first one, 2. So if I thought I have 3, I've filled the 2 in the first one. I'm left with a balance of 1. So the next one is going to go into the next row. Okay. That's how we wrote the electronic configuration. Then we went to something else here. Carbon also. Carbon has 6. The first room is going to take 2. The next room, the balance is going to be 4. Can the 4 fit in the next room? Yes, they can. Why? Because the room can take a maximum of 8, but anything less than 8, it can be there. So when I go to this case, sodium has what? 2, 11. I first pick the 2. What is the balance? 9. When it's the balance,
the balance
is 9.
9. But to go to the next
Again, 9 cannot be put there. It's 2 to 8 to 1.
2 to 8 to 1.
Yeah.
9.
People, the reason why I've been telling you, here the way you fold pattern, some things you call them obvious, but most of the cases people fail to write them. I'm saying that 11 electrons, the first room took 2, the next room can take 8, so that is 10. What about the remaining 1? The 1 can be put in the third room. So when you go to this one here, let me just take this one here. Looking at this one, all these electrons here, please. I'll be supposed to mute everyone here. So I was going to say that I've just selected a few elements and I'll prove you how to write the electron configurations. What do I mean by attaining stable electron configuration? What do I mean by having a stable electron configuration? You say a stable electron configuration is the one in which all the energy levels are fully filled. What do I mean by fully filled? Every single energy level must be carrying the maximum capacity it must possess. We say that the first one can afford to carry 2, the rest can carry a maximum of 8. Look at the first element here, hydrogen here. Hydrogen has only 1, but this first energy level is meant to carry a maximum of 2. So meaning that hydrogen requires a balance, needs a balance. Let me just say balance. Needs extra. How many extra electrons do I need to make this hydrogen comfortable? Since the first one must take 2, this one requires a balance of 1. This one here, what do you look at this? Look at this. This one, the first one has 2. The second has only 1. But for the second one to be fully filled, it must have how many? 8. Not 8. So 8. Out of the 8, you only have 1. So that means that this guy has a balance of 7 to fill. 7 electrons. What about this one here? Requires a balance of what? Out of the 8 has only what? 4. So it's going to require an extra 4 to be fully filled.
4 electrons.
You get it, huh? So when you look at this one here also, here, this one is fully filled, that one fully filled, but this one has only 1. So this one has to have a maximum of 8. It requires an extra 7 to be fully filled. The same applies to
electrons.
This one is going to require an extra how many? It's going to require an extra 5 to be fully filled. This one is going to require an extra how much? 2. So now meaning that here, extra 2 to be fully filled to attain what they call a stable electron configuration. Where is it going to get all this? Because these extras that I'm trying to say are the ones that are going to create demand. So this element, this table, to have what we call a fully filled energy level, it must be looking for these electrons. Where is it going to find them? Where are we going to locate them? The reason why we are going to be bombing. For us, in order to attain the stable electron configuration. In attaining the stable electron configuration, we shall be finding extra electrons. How? these things are going to be having. So, all bonding together. So now, what are we going to do in this case? Bonding. Elements, atoms are going to be combined together with others. For what purposes? Such that they can attain a stable electron configuration. It's the first purpose. How are they going to do it? That's why we're going to look at the different types of bonding. We shall have 5 or about 4. At your level, we shall discuss about 5 types of bonding. And we shall be looking at how they be. So now, when you require 2 electrons, are you going to have the same demand as that one that has 7, that requires a balance of 7? The demands are going to be different.
Pardon?
I'm trying to say that when you look at the demands, the extra electrons that each of them was needing, others are requiring 1, another one 2, 5, 7. Even there are those ones that can require extra 8 or something like that. So, do you think that they're going to bond in the same way?
Teacher, we are not hearing.
You can't hear me. Wow.
Mama teacher, we can hear you.
Okay, I was trying to say that here. When you look at the extra electrons required, there are so many. Each one requires different amounts, but those different numbers are going to bring us to the different types of bonding that you may need to have. Okay, so now, talking about bonding, types of bonding, we shall have 1 types of bonding that we shall have here. Anyone who can
Covalent bonding.
Electrovalent.
there is what they call
Ionic bonding.
electrovalence, which is the same as ionic bonding.
Covalent.
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 You guys go back.
Covalent.
It's not covalent, it's covalent.
Covalent.
It's covalent. There is no N. Okay? Types of bonding, covalent bonding.
Van der Waals.
Covalent.
We have someone saying
Van
metallic
der Waals.
bonding.
Van der Waals
Ionic.
forces.
We have van der Waals process.
Ionic bonding.
We shall talk about it, but it's going to be falling under here. Yeah? Okay?
Ionic.
So, ionic is the same as electrovalent. Huh?
Excuse me, teacher.
Yes, my dear.
Could you please mute all of us because some people keep muting themselves?
Okay, I'm going to do so. Thanks for requesting. Is this such
Now
to record?
you're the one who's singing. Keep quiet.
Guys, we control each other because we do believe that we are of age to understand.
Where are we? I am not on.
Okay. So here we are saying that there is also what they call dative bonding. We shall also call it coordinate bonding.
So we cannot see you.
You can't see the teacher.
We can.
Okay. We shall have dative bonding.
I'm a teacher, we can.
We shall also talk about another one that will be so special, which we call hydrogen bonding. But the first ones, the first 3 are going to be important here. Okay? And I'm going to see how we can summarize them. Okay? So now, here, let me start with what, which is going to be very easy. We start with the metallic bonding, going downwards. Huh? So metallic bonding is going to be the first on the table. And we're going to see how we can make the understanding. We don't need to rush, because remember, this is the chapter that opens all the entire doors of chemistry. When you fail from the atomic structure, chemical bonding, your life of chemistry might become a little bit harder, way much harder than you expected. Okay, so here I'm going to start all the types of bonding I've been listed. I'll start with the metallic bonds. bonding. Because what it is about, bonding is all about chemical combination of two or more elements, chemical combination of two or more atoms or elements like that. But now, what do we know about metallic bonding here? This bonding one is going to occur because from metallic bonding, it only occurs between metals. That is the first part, occurs between metal atoms or metal elements between metals, like that. And then another thing, if it occurs between metals, how do metals do? Does it involve transfer of electrons? Because what do you know about metals? Metals here, another thing here, look at this. If it occurs about metals, how can you identify metals first? Before you go to go, how do the atoms of metals combine? Metals here, for you to know them, one, always, after writing, for you to identify that an element is a metal, what simple things can you have? How do you identify identification? How to identify elements that are metals? Identify elements that are metals. Can you identify them simply? How do you identify them? The easiest way to identify elements that are metals, one, always after writing their configurations here, they tend, one, metals tend to have one to three electrons on their outermost energy level. So after writing the electron configuration of a particular element, what are you going to do? Always look at the level, the last level that you feel. If it always has electrons that it's either 1, 2, or 3, most of the cases, that element is meant to be a metal. Is meant to be what? A metal. Except who? Except hydrogen. Except hydrogen. All others that you are going to find in your periodic table that have 1 electrons that tend to have 1 to 3 electrons. When I say 1 to 3 electrons on their outermost energy level, they all identify them as metals. So now my task is for you to tell me which ones are those. Yes, please.
Sodium.
I'll talk about hydrogen in a special. Let me first talk about the first things. Examples of metals. You must be. Examples. And by the way, another identifier, always, since when you are giving groups, you say that the number of electrons that you find on the last level are the ones that we use to give or predict the groups that element belongs to. When you find an element that has only 1 electron on the last level, or 2 electrons on the last level, or 3 electrons, those elements will be belonging to which groups? Either group 1, group 2, or group 3. That is another way. These metals always belong to what? Always tend to belong to what? Tend to belong to group from 1 to 3. And also which other groups? Also the transition metals. Also you have what they call transition metals. Transition metals. Do you remember those transition metals? They tend to be in group 1. Hey, here you might not see it. We say that they tend to belong to group 1, 2, and 3. And also you have what they call transition metals. Those transition metals, those are the copper, the lead, the zinc, the iron, the manganese. I think you've heard of such elements. Huh? Those are all metals. Examples. Yeah. The first ones, before I go to
Magnesium.
the first one, we have magnesium, magnesium,
Sodium.
sorry,
Sodium.
we have lithium, sodium, barium, you say
Potassium, boron,
Aluminium.
boron,
we have aluminium, we have what? Potassium,
sodium,
we have sodium, sorry,
Chlorine.
we have what?
Carbon.
Remember the rules. Not whatever should cross your mind, you should mention it. We have already, the reason why I gave you this summary is that out of the many that you have in the head, can you select those ones there that tend to have after? That means that for you to give me this example, the best way that you have given me these examples is for you that you have somewhere that you wrote electron configurations, which I really know that you do have. You just go and check and see, okay, can I look at the last levels? Which one has 1 electron on the last level? Which one has 2 electrons on the last level? Which one has 3 electrons on the last level? So the ones that I'm taking in here, you're going to write their configurations. For example, the configuration of boron is what? 2 to 3. Are you seeing that it qualifies to be? Are we there?
Yes.
Lithium. When I go to which other? When I go to potassium, it is 2, 8 to 8 to 1. Does it qualify? Yes, the last level has only 1. Are you getting what I'm trying to say? When I go to beryllium, I have 2 to 2. Are we there? The last level has only what? 2 electrons. So that's how you identify elements that are metals. I'm going to talk about others such as the transition ones, the zinc, lead, and what. All of these also qualify to be metals, but they're going to come in handy later. But before I go to that, we have already.
calcium.
Yes, we have also calcium. Yes, we do. Calcium belongs there. Calcium is there. So now, calcium has to also. Now, when you look at the demands of these guys here, you are going to find that either, let me show you something, because I want you to understand it, not to just rush through it. Amongst these elements that you have given me, we're going to look at why do they tend to bond with each other? They tend to bond with one another. How? To attain a stable configuration. Let me just summarize this. We have the lithium here, we have the sodium, and the potassium, isn't it? And I'm going to have another one. I'm going to have the beryllium here. I'll have the magnesium. That is another, the next group, calcium. Boron, and then what?
Boron. Aluminium.
Isn't it? Huh? So, these first 3, all of them have only 1 electron, isn't it? Huh? 1 electron on the last level. Do you agree? Oh, to show you, some people may not get it. This one is written as 2 to 1, 2, 8 to 1, 2 to 8, 8 to 1. Are you seeing that? These ones here belong to the same group. This one is written as 2, 2, 8, 2, 2, 8, 8, 2. Are you seeing that? And these ones are in the next group, boron and aluminium. This one is written as 2 to 3. This is written as 2, 8 to 3. Do you agree, guys?
Yes.
Good. Remember?
Yes.
Yes.
Yeah.
Yes.
Lucy, please. I'll say that the reason why they belong to group 1 because they have only 1 electron on the last level. For you to be given a group, a particular element, any element to be given a group, you must look at how many electrons do they have on the last level. You get it? So now, let us look at the other thing that I talked about, attaining electron configuration. How would you think that these metals would get their balances? Which extra electrons do they need? When I look at group 1, they require a balance of 7. Do you agree? Because each level here, these levels here that are left with, for them to be fully filled, they need to be 8, isn't it? So these ones here require a balance of 7. How many do these ones require? Group 2? Can everyone see that they require a balance of 6? People, is it okay?
Yes.
Why do they require a balance of 6? Because they need to add 6 electrons to have it as 8. That's what they call a fully filled. These ones require a balance of what? 5.
5.
Isn't it?
Yes.
Where are you going to find someone who is so generous to give you this many electrons? You cannot find such people. Out of the entire 8, you only have 1. It's like saying that I need a million, I only have 100 shillings. That's where a lot of hope. So what do? These metals here, they always require more electrons to attain that. What do they do instead? Since they cannot afford to find members to help them out to get an extra 7, an extra 6, an extra 5, what do they do instead?
They
For
lose
them,
electrons.
They lose electrons.
they tend to what? Lose, not gain. They only do one thing. Metals, what do they do? Here, I want you to realize it. Because the demand is too high. 7 electrons. Who is going to give you the 7 electrons? Who is going to give you the 6 electrons? Where can you find the 5? So instead of, for them, what do they do in their way? They either tend to lose them. They tend to lose what? Them.
Then
So when they give them away, and when they give them away, we shall talk about something else. So what have we noted about metals? Metals tend to lose electrons. Lose their what? Their outermost electrons. Outermost. Why do they lose their outermost electrons? Such that they have a stable electron to have, in order to have or to attain a stable electron configuration. Are we there? So meaning that instead of these ones, look at this case. Instead of the group 1 elements getting an extra 7, I rather lose what is making me feel uncomfortable. What is making them feel uncomfortable? The extra 1 electron here. When they come, they will lose the 1 electron. So when they lose the 1 electron, that means that they are going to be left with only levels that are fully filled. That are fully filled. Are you getting me, members? How? Let me see. Look at this. Lithium was initially having 2 to 1, like that. But after it's intending to lose an electron, when it loses that electron, it's going to have a positive charge. Have you ever heard of that thing? Yes. How? It has lost this electron away, so it's going to be left with a 2. Look at potassium here. Potassium was initially as an atom 2 to 8 to 1, but after that, it's going to lose one electron, and then it's going to be left with 2 to 8 to 8. But here it's going to possess a positive charge. Anyone to tell us why do we put a positive charge there?
Because it has lost.
Because it has lost electrons.
And electrons are negative charges.
Yes, electrons are positive charges, but why does it have a positive charge? Yes?
To indicate that it's a metal.
Indicate that it's a metal?
Teacher, because it has become because it has attained its electronic configuration, it's now a stable one.
No. Yes, Peruf?
Because it has lost only one electron.
Excuse me, teacher.
Yes?
I think because the metals have more protons than electrons.
Absolutely. Thank you so much. She has nailed it. She has said because after losing, look at this. Remember, I want us to join facts easily. Yeah? Let us not be rushing. Yeah? We are saying that why is it going to attain the positive charge? Most before it was an atom, it never carried anything. Look at the symbol. There is no sign of it. Whenever I write a symbol without any sign, like negative or positive, what does it imply? It implies within it, we say that elements do, or atoms do have positive particles, which we call protons, and then they have negative particles that we call electrons. An atom, we say that the reason why it is neutral, you know the meaning of neutral? That it doesn't take any sign, whether to be positive or negative. Why? Because the particles that it's holding, they're equal in number. The positives are equal to negatives. It's like, are you having good deeds that are equal to your negatives? The sins are equal to the good deeds. What do we typically say that you're good or bad? No, because the amount of positives are canceling out the amount of negatives. But now, after losing one side, because look at this, your positives are not being lost at any one time. What you are losing are electrons. When you lose the electrons, you are going to create an imbalance. What is going to remain behind? After me losing this extra one electron here, we are going to be remaining with protons that are more than the electrons. By how much? They're only by the amount that you have lost. When I lose one electron, that means that I'm going to remain with one extra proton. Before, the protons were equal to electrons. When I lose electrons, the protons are going to remain much more many. So now what happens here? Metals tend, we have said that, they tend to lose their outermost electrons to attain a stable electron configuration and also form what? They form positive
Recharged ions.
positively charged, which is called what? Cions. One, another note here, they form positively
Charged ions.
charged ions, which you call what? Cations. Are we there? Positive charged ions that have a charge equal to the number of electrons, So meaning that if a metal loses one, it's going to have a single positive charge. A single positive charge. Do I need to put a positive charge here? A one? No. When I have one, you just put a plus sign. You get it? When I have two, the two I need to indicate it. When I have a three, also I need to indicate it. So I've said that they tend to form positive, and then that are equal to that. Reason why do they form the positive charge? I don't want us to forget it. I think I can take away this. The reason here. Why? Because the cation has more what? That positive ion, which I can call the cation has what? Has more protons or protons than what?
Electrons.
Electrons. The form particle. Yeah? So those are the things that we summarize. We need to build together, and you see, hey, those are things they ask in question. And you find people do not understand. We started, why are they forced? They are forced to use electrons because they require a lot of electrons to be fully filled. Well, who is going to give you the extra 7? The only way they are going to do that is to lose the outermost electrons to attain a stable electron configuration. Are we there? And then after that, what do? They form positively charged ions, which you call cations, that have a charge equal to the number of electrons lost. Okay? And the reason here, why do they possess a positive charge? Because the cation has more protons than electrons. Are those things too hard?
No.
You're the one. You moved, then you went and looked. These ones here are going to be, where are you going to find them? In ion formation. How do you form ions? So that means that I've helped you revise that part. Here, how can I write these ones here? These magnesiums here, they're going to lose 2 electrons. For example, I'll have beryllium. After losing 2 electrons, it's going to be beryllium ion. And by the way, something, how do you name these ions here? The only thing for metals, when to form their ions, it retains the particle they form after losing. It has the same name as what you had before, but the only thing that you're going to add is the word ion. Positive ions, you only just need to add the word ion. Let's say this was potassium, so this will be potassium ion. This was beryllium, this will be beryllium ion. If I thought this was magnesium, the other will be magnesium ion. Are we together? If I thought I had boron,
Yes.
both boron ion. It was aluminium, it will be aluminium what? Ion. So here, that's what we need. So what are we going to find out? Is the equation I've written, but that means that each of you here can write for me the ions formed by these metals. So this one say it will be lithium ion, that will be potassium ion, let's say calcium ion, and then beryllium ion. You can fill up the missing gaps, aluminium ion, like that. Huh? I'm giving you the formulas. How do you convert this one to this? By this atom has to lose how many electrons? 2 electrons. You must know that. Also the same thing here. For you to convert aluminium atom to aluminium ion, what do you need to do? The aluminium atom has to lose how many electrons? 3 electrons to attain this aluminium that carries a positive charge of 3. Are we together, members?
Yeah.
Yes.
Okay. So now let me go to
Yes, teacher.
Okay. So please don't to ask me questions. Huh? You raise and ask a question. You feel like you are not understanding. Yes, please. So here I've helped you revise the ion formation. Can I now talk about what would happen? Excuse me. I was trying to say, what do you think would happen when I have atoms of lithium alone? How will they bond with each other? This is where the gist of the matter. This is why you're going to understand metallic bonding. Just a moment.
Okay.
Okay. I was trying to say that, members, I want us to understand metallic bonding. Everything about metals you have understood. Let us talk about what would happen if I told you have only atoms of sodium, atoms of potassium alone. How do they combine with each other? Does each of them have to lose? To lose to what? Let us look at this. How do atoms of metals bond? How do they bond? I'll start with, I've written this. A, the first scenario, atoms of the same element. Same element of metal. That is the first scenario. We are wondering, how do the atoms of metals, let's say I have atoms of sodium alone. How can I force a particle of sodium to combine with another particle of sodium? Remember, each one of them is having an electron. Sorry. Remember, each one of them has an electron to give away. Do they give to each other? No.
They
What
share.
happens? Are we together? Do they share? No.
Yeah.
What is going to happen here? When you have, let's say, what I'm trying to say here, I have sodium, let me just use lithium. Lithium and lithium atoms. This one has 2 to 1, and also this one has 2 to 1. How are they going to bond with each other? This one, remember we say that metals are meant to give away.
Transfer.
And also this one is going to be giving away. Are they going to give away? So this is where things are going to get a little bit. They're not going to confuse, by the way. It's going to be very simple. It's like this one is rich, it can give away, and also this one is rich to give away. How do they gain stability? Since they cannot find any person to accept this extra 2, because look at this. When this one gives away the 1, this and also this one gives away the 1, what is going to happen? Is there any person
They
ready?
transfer.
They won't transfer.
They become an ion.
What do they do? What they happen to do, look at this. Pay attention. Let me try to do that. Let me say that this is the atom of lithium. This is one particle, and another particle of lithium, let's say. What they rather do, they'll always try to tend to lose them, each one will lose its 1 electron, but that 1 electron is not going to be lost far away. The electron is going to be lost. Let's say an electron is going to be lost from this one here, 1 electron, and also another electron is going to be lost. When it is lost, it's going to have a positive charge, and this one is going to have a positive charge. Are you getting me? But now, these electrons are not going to move far away. They are going to keep around in this region around, moving along the surface, such that at any one time, this one can take it back. take them back. I repeat this one here. Listen to this. Each atom, it will lose its outermost electron, leaving behind a positively charged ion. Are you saying this is positive? But now the electrons that you're meant to be losing here, these electrons are going to remain moving around. Moving around means they're going to be mobile. Or what they call, have you ever heard of what they call delocalized electrons?
No.
Delocalized.
No?
Have you heard of it?
Yes.
No.
It means that you
No,
are,
teacher.
you have it, huh? It means free and mobile. Free and, it's like now, at home, most of us can be free. You can do whatever, but you cannot move outside. You can be free, but not mobile. While others, they can be so free, even they can manage to go out anywhere, to manage any plot they can be having. So those are what they call delocalized. But now I want you to understand simple by a facts combining them simply. This lithium, remember, it was meant to lose one electron, not so? Each atom is going to lose an electron, but that electron is not going to be going anywhere. Remember, it cannot be transferred to this guy, and also this guy cannot transfer. So it's going to remain along the surface, revolving, moving around, rotating about this positive ion, huh? Meaning that at any one time, it can be taken back. So the reason why these electrons are moving around, they become delocalized electrons. And by the way, is the major reason why you find that metals conduct electricity. Why do metals conduct electricity? Electricity is always carried by these electrons here that are moving along the surface. So it's the one that enables the metal strip to carry electricity from one point to another. Are you getting it? So that's why we have these delocalized electrons that you have at the surface are the ones that make the metal to be conducting electricity, and by the way, heat. And the heat. Because they keep on transferring the heat from one point, there's somewhere they transfer the what? The electricity. So that's the science we have for you here. So what have I said in simple facts? When you have atoms of the same element, metals, when they are metals, each metal atom, let us write it such that we don't forget, because we can talk a lot and forget. You say that each metal atom loses, each metal atom loses its outermost, I think you cannot say this, like its outermost electrons that become delocalized, Have you understood the meaning of delocalized? Free and mobile. If it's hard for you, you just say free and mobile, delocalized, leaving before delocalized within. So now, just remember, these particles are so close to one another. They form what they call a metallic lattice. It's called a metallic lattice. I'm going to draw it for you. So here, become delocalized within the metallic lattice. Metallic lattice. That cluster of them is going to be called metallic lattice. We underline that one there. Each metal atom loses its outermost electrons that become delocalized within the metallic lattice, leaving behind positively charged particles. Leaving behind positively charged particles. Ions. Can I call them ions? It's called cations. Surrounded by the free mobile electrons. Surrounded by the free mobile electrons. Yeah. So, what do you know about metals? Things that I want you to know about metals. Metals, they form what they call metallic lattices. What is made up of the metallic lattices? A metallic lattice has positively charged ions surrounded by free mobile electrons. Free mobile electrons. An example, we can take, I'm going to take an example of what? Group 1 metals. Eg, group 1 what? Let's say group 1 metals, because each of them, group 1 metals, an example. How do I do the analysis? Every single atom is like that. I'm just taking, they're forming a cluster. And they shouldn't be intersecting. The circles, they should be independent. I'm sorry about this. You know something that is relative. But we say that, I want you to first pay attention here before. I say that for group 1, each one is allowed to lose 1, not so? So I'm trying to say that after losing, it's going to leave behind something that is going to carry a single positive charge. And the electron is going to be along the surface here. Like this, like that, like that, like this. Each one. That any one time, if at all it's forced, it can, that electron can go back and then it cancels out the positive charge. So now what did I say about these electrons? These electrons here are the ones that are free and mobile. They can rotate within this lattice. So what am I trying to draw here? This one here is what I call the metallic lattice, the entire thing. Metallic lattice. So what is in this metallic lattice? We see many positive ions, possibly charged ions, surrounded by free mobile what? Electrons. Are we there? So now, meaning that these atoms are going to be clustered together, bonded to one another. What makes them stronger? The positive charge and the electrons that are around them. By the way, the strength of this the metallic bond, because the way they are connected to one another, they form what they call the metallic bond. So now, which one is going to be much stronger? That one formed by group 1 elements, group 2 elements, or group 3 elements? What would you think? Here, in group 1, only one electron, each atom here, each atom here was allowed to lose only 1. What if it was allowed to lose 2? What if it was allowed to lose 3? Would the strength be the same? For example, if I say magnesium, how can I modify that one for magnesium? You only just put, because magnesium can afford to lose how many electrons? 2. I just put a 2 here because it's going to form 2 plus, not so? So I be changing here 2 plus, 2 plus, 2 plus. That is for group 2 elements. So, but now, how many electrons each one is losing? I add an extra one here. I want to ask a simple question here. We are saying that metals are rich, they can give away. Which group would you prefer to be in? If you have the first group, each member has an extra million on them. That is group 1. Let's say that this one has an extra 1 million. The other group has an extra 2 million. Another one has an extra 3 million. Which groups would you suggest to be into?
Group 3.
Group 3.
Yes. So what do you
Group
get?
3.
Yes.
Group 3.
If it's group 3, it means that the strength, the one that can provide more electrons within the metallic lattice, is the one that is going to have stronger metallic what? Bonds. The one with as many more, the one that can lose more metals, meaning that here, what are we going to note here? Initially, I drew for group 1. I've drawn that one for group 1, group 2 here. You can also draw that one for group 3. But here, will I ask you to draw that one? I'm only just drawing it for you to understand it much better. What we note here, the strength of the metallic bond increases with increase increases with increase in the number of electrons contributed by each metal atom in a metallic lattice. So, what am I trying to say? The strength of the metallic bond here increases with increase in the number of electrons contributed. I've skipped something here. Contributed, allow me, contributed by each. Here there is a word contributed. Huh? I'm saying that the strength of the metallic bond increases with increase in the number of electrons contributed by each metal atom in the metallic lattice. Meaning that which metals are going to be having stronger metallic bonds. So you're going to find out here, what are you finding out? That group 3 metals have stronger metallic bonds, form stronger metallic bonds than what? Group 2, and group 2 are going to form stronger metallic bonds than group what? Group 1. The one that has more electrons, that can contribute more electrons, is the one that is going to be much more stronger. So in this statement, what can we summarize here? I've told you here that the bonds, the metallic bonds formed by group 2 elements, group 3 metals will have stronger metallic bonds than those of group 2 and those of metals. Are we together? For example, what do I mean here? Let me show you. We have heard of, yes please. Someone is, the hand is up. Elizabeth?
I was asking, like in the exam, in case they bring metallic bonding, like do we use the metallic lattice or we use the other first one that you used?
Which one? Hey, the other equations that I wrote.
No, like the first diagram you used, the one like where you put the mobile, the mobile electrons like outside.
I've drawn this one here better. This one will be much better.
Okay.
Much better. Okay, so now I was trying to say as we wind up here, and now need to finish up, you're going to find this explains to show you the strength. Let me give you aluminium. Aluminium is in group 3. Have you seen aluminium foils at home that they use for wrapping? Those are spoken. Aluminium foils. Have you seen the magnesium ribbon?
Yes.
And then you're going to see another one to show you that the strength of these forces is so big. It follows this one here. Let me give you sodium. I think anyone in senior one, you ever seen a piece of sodium? This aluminum foil is so strong that it can retain, it is too strong, it cannot easily be cut. But when you look at a magnesium ribbon is not as strong as the aluminum foil. It can easily be, as you see this piece, it can be as a simple wire that you can break at any one time like this. I think you ever seen the magnesium ribbon. Have you ever seen the magnesium ribbon numbers?
Yes,
Okay.
teacher.
The hang line. It's like you see as the hang, the wire you hang your clothes. That's how it appears. It can easily be broken. It's not so strong like the other ones. It can easily be broken. And then this sodium metal is like, as you see ghee, as you see this ghee butter or blue band, it can easily be cut by a knife. Why do you find that the sodium is so soft? This one is relatively hard, and this one is the hardest. The reason why the aluminum foil is hard, because it forms stronger metallic bonds than magnesium that is relatively hard. And then sodium is so soft and can easily be cut by a knife. Why? Because it forms weaker metallic bonds. Have you seen that, members? What brings about the difference in the strength? It all depends on the number of electrons each metal atom can give away. So the more it gives away, the harder it becomes. So finally, what will be the properties? Because I don't believe that I'll be coming back and talk about metallic bonding again in the same regard. Okay, I'll talk about, when we talk about alloys, I think it will pass by that when they're so different. So here, what do you note about this kind of arrangement? When you look at properties of metallic bonds, compounds formed by metallic bonding, are you finding that the particles are so close to one another? They're very compact. They're too compact to one another. Remember in senior one, we say that whenever the particles are far away from one another, when they're so close to one another, they always help you to predict what kind of physical state that substance can be. Always, substances formed by metallic bonding, how do they appear? Properties of them. Properties.
They are solid.
Properties, they are properties, okay. One, they are always existing as what? Solids at room temperature. Solids. Normally, you find them as solids. They are always solids at room temperature and pressure. But also there is only one metal that is a liquid, except what? Mercury. Mercury is the only metal that is in liquid form. Except what? Mercury. All metals are going to find like that. Another thing that I told you about them, do you think that whenever you have these particles that are so arranged close to one another, when you need to break them down, and I've told you the strength of these bonds here, how they are connected increases the number of electrons. Do you think that they're going to be easily broken down? No.
No.
You require a lot of heat to break these particles that are arranged in this way, to break them. That's why you find, compared to any other type of bonding, the energy that you require to break down these substances that are bound through metallic bonding is going to require a highest, they'll always have the highest bonding and melting points. Because for you to break them down, you always need a lot of effort. So always compounds formed by metallic bonding, they have the highest, compared to other bonds, they have the highest melting
Point.
and wait, what? People you do not need to travel. Let us understand that they always have the highest and lowest. So the highest are melting and boiling one. Why? Because you need extra energy to break them down. The third one, before I finish, yes, please. Yes, that is the next one here. Someone say that Remember these electrons that keep on moving around, they are the ones, since they're going to be good conductors. Very good conductors. Good
Of
conductors
electricity.
Heat.
of heat and
Electricity.
why? Because they have delocalized what? Electrons within the metallic lattice. So those are the three major properties of metallic bonds. And with that, is there any question before we call it a day?
Teacher, what is RTP?
Yes, please.
What
Hey,
is
at room
RTP?
temperature, is RTP at room temperature? Room temperature and pressure, I'm sorry.
Oh, thank you.
Yeah. Is it okay?
Excuse me, teacher.
I'm listening.
Can you say
Teacher, what is the solid?
What is that? Okay, I'll show you some properties of compounds. Compounds formed through metallic compounds. Properties of metallic compounds. Metallic.
Oh,
All compounds formed through metallic bonding. What do metals behave like? They're usually solids at room temperature. They have very high, very high. They have the highest melting and boiling what? Points compared to any other type of bonding that you're going to talk about.
teacher? I have.
Yes, please.
Can you say they have high density?
Oh, okay. I've forgotten about that. Thank you. Let me explain to that. Why do they have high density? Also, they have high density. High density, what do I mean? They're always heavy. They have high density. Why do they have high density? Since there are many particles that are so close to one another, you're going to find that in a small volume, you're going to have many particles in one unit like this, 1 centimeter here. You're going to find many particles clustered together. That's why you find that most metals have very high what? Density. They are very heavy. Too heavy. That's another one. The fourth one. They have high density. So one thing that
Teacher,
yes, please.
teacher,
Yes, please.
what's the word in between electrons and bi on the notepad?
Contributed by each. I told you that I skipped it. Contributed by each metal. You get it?
Okay, thank you.
What is going to be left in the next meeting that if at all will be there? We shall look at how do these atoms, what will happen if at all I don't have atoms of the same thing? Let's say I have sodium and magnesium. How can magnesium combine with sodium? They are both metals. How do they combine with each other? You get it? So we shall discuss about that, and we shall talk about things such as alloys. I don't believe you ever heard of them. What is an alloy? You get it? So it's going to be just in that same instance. Okay. After that, probably it will be done. That will be done, and then I'll be capable of crossing to another type of bonding.
bonding.
Is it okay? Yes, Elizabeth?
Yes.
Teacher, on the
Excuse me,
teacher, on the note, is it okay, like if you say the strength of the metallic bond increases, like is it okay if you be like the strength increases like with the number of electrons lost?
Lost by what?
Like like the ones that are lost like during, like when it's 2 to 3,
What I'm trying to say, yes, what you're trying to say is close to the truth, but you need to be so particular with your statements, my dear. Yeah, we need to be addressing them like you say, lost by what? By every single metal atom, by every single metal atom. It can be okay.
Okay.
Yes. Good conductors of heat and electricity. That's what we said. Someone's asking. So, is that okay, Atim? Please, I think you'll be the last one.
Teacher, my question is, we have not yet done, what is it called? Those things of equations, because like I see most people in other schools have.
You're so much right for nothing, my dear. Too much right for nothing. So what I can tell you that it will depend on our speeds here. After chemical bonding, the next thing that you do is called chemical formula. You'll be comfortable with formula, and then you talk about chemical equations. So after this one here is where you go. So that's why I'm saying that you don't need to worry at all. It's going to be
Okay,
all about your.
Okay.
All right. So can we call it a lesson?
Yep.
Yes, teacher.
Yeah,
Thank you, teacher.
Thank you, teacher.
When we talk about